Hey everyone, welcome back to Take You Forward. Today we will be solving the 23rd problem from the dynamic programming playlist, and the problem goes as Unbounded Knapsack. So what does the problem state? By the way, in order to understand this question, you should have seen the problem 01 knapsack, which is the DP 19. So please make sure you watch 01 knapsack. Okay. So how is unbounded knapsack different from the 01 knapsack? So over here, there is a thief, right, who goes into the house with a bag weight of 10. Okay. And there are items. First item has a weight of 2, and if he steals that item, he gets a value 5. The second item has a weight of 4, and if he steals that, he gets a value 11. The third item has a weight of 6. If he steals that, he gets a weight of he gets a value of 13. But the difference from, like, how is this problem different from 01 knapsack? Let's understand this. So in 01 knapsack, it was clearly stated that there will only be one occurrence. Yes, I repeat, there will only be one occurrence of these instances, right? But over here in unbounded knapsack, it states there are infinite supply. Yes, infinite supply. Against, similar to the previous question, coins in DP 22 and DP 20 that we did, similar to that problem where we have been stated that, hey, listen, there will be something as an infinite supply of every item. That means you can pick a single item as many times as you wish. Like, for an example, if the thief comes up with a weight of 10, he will be like, okay, I can pick someone with a weight 6 and a weight 4, and this will give me 13 plus 11, which is 24 value. Or someone can be like, hey, listen, I'll pick the weight 6 once, and I'll pick the weight 2. I'll pick this twice, and if I do this, this weight 6 will give me 13 value, and this 2 is giving me 5. So 5 cross 2 will be 10. So 13 plus 10 will be 23 is the value that I can get. Or someone might be like that, hey, listen, I'm going to pick two items of weight 4. Yes, two items of weight 4 plus one item of weight 2. So if I'm picking two items of weight 4, it will be 11 cross 2, which is 22. One item of weight 2, which is 22 plus 5, 27. So in this way, you can actually pick up in a lot of other ways. Like, you can also say that, hey, listen, I'm going to pick the weight 2 5 times. 5 times, because if I pick up the weight to 5 times, that will be equivalent to the weight 10. And how much value will I get? 5 into 5, 25. So there can be numerous ways, and you see that this value that you get is the maximum possible value. Yes, is the maximum possible value, and that's what is going to be the answer, right? So I hope that makes sense, the question. So how's this question different from 01 knapsack? It states you have an infinite supply, right? So again, you'll follow the pattern of knapsack, and I've clearly stated what is the pattern of knapsack. You have to write a recurrence, and in order to write the recurrence, express everything in terms of index, weight, explore possibilities. Yes, explore all possibilities. And the knapsack states what is the maximum value that you can generate. So return the max of everyone. Return the max of everyone. Every possibility, rather. That's what you will simply do in order to solve this problem. So let's quickly write down this recurrence. So index and weight is the initial one. So basically what I'm saying is, okay, so if there are three items with a particular weight and a particular value, I'm saying till n minus 1 with a baggage weight of w. That means till here with the baggage, like till here n minus 1 with a baggage weight of w, what is the maximum value you can generate? What is the maximum value you can get? So this function will tell you till n minus 1 with a baggage weight of a w, what is the maximum value that you can generate, right? So what I can say is f of index w, right? So let's forget about the base case. Now let's think about what are the cases. Knapsack had a couple of cases, right? Where he say that, okay, I'll not take this guy, which is I'll not pick this guy. So if I don't pick this guy, I will have a value addition of 0 to myself. I'll have a value addition of 0 to myself. And if I'm not picking this, I'll definitely move here and the weight still stays the same. Again, very simple. The take will be 0 initially, but I'm looking for maximal value. So if you remember, it will always be int mean. Okay, now when can I pick it up? Again, very similar. I can only pick up if the weight of that guy is lesser than the bag weight. Yes, is lesser than the W, which is the bag weight. Then only I can pick up. And if I'm picking up, can I say the value addition will be value of index plus function of W minus weight of that guy's index. But what happens to this particular index? Again, similar to the previous one, it stated infinite supply, and whenever it is infinite, you stand at the same index. Previous question. Yes, because you can again pick up that guy. So kindly stand at the same index. You don't need to do anything. Kindly stand at the same index. So I'm standing at the same index, and then you just need to return the max of take and the max of not take. So once you have done this, that's perfectly fine. Now you need to write the base case. So how do you write the base case? So remember guys, in all the infinite supply unbounded cases, the main point of concern is whenever you try to pick, you still stand at the same index because you can go on picking. That's the crucial point. So what about the base case? As I said to you, whenever you start from n minus 1, the base case that you write is for 0, right? So whenever you come to 0, yes, whenever you come to 0, always try to think in this case. Okay, this is 0. This guy probably has a weight of 3, and this guy probably has a value of 10. Okay, and the thief still has a weight of 8 left. Like thief's baggage weight left is 8. So if I ask you, how many times can the thief steal this item? Because he will obviously steal. There is only one item left and he still has a baggage weight of 8. So it's very obvious that he's going to steal this guy. Like, why will he not steal? Logically, he will always steal it, because if he doesn't steal his, because this is the last item. If he does not steals it, it will be his loss, right? So if the weight is 8, what will he do? He'll try to steal it. That's for sure that I will say, hey, listen, I am going to steal it. No matter what happens, I am going to steal it. So how many items will he steal? Because I know this guy is having an infinite supply. So he'll be like, Striver, if he has a weight 8 left, he'll steal 2 items. Because this has a 3 guy, so he'll steal twice. If this was somewhere around 13, he would steal this 4 times. Make sense? If this was somewhere around 2, he'll not be able to steal it. So can I say whatever bag weight by the weight of 0 is the number of times it can steal? Can I say this? Assuming that it will always have a weight, which is definitely, because every item has a weight. None of the items can have a weight 0. So can I say this is the number of times, like the integer will be the number of times it can steal it? If it is 8, then I'll have 8 by 3 saying 2. If it is 13, then I'll have 13 by 3 saying 4 into what is the value that it will add? Value of 0 is what it adds. So can I say this is what the base case will be whenever you reach the end? The answer for a single array is this. Again, very simple. So can I say this? If I reach index equal to 0, I'm going to return a quite simple W by array of 0 into, or rather weight of 0 into, like you can do an integer of this, into value of 0. And this is going to be my base case. Amazing. Perfect. So if this is the base case, after this, I think your recurrence is ready. And once the recurrence is ready, again, this I have been talking through, the time complexity will be exponential. Why not 2 to the power n? Because of this case, you're standing at the same index. And what about the space complexity? Auxiliary stack space will be the bag weight. Why? Assume you have weights of 1, 2 and another 1. Okay, assume you have weights like this. So this is a weight of 1 and you had a bag weight of 10. So you'll be like, okay, 10. If you pick up, that will reduce to 9. If you pick up, that will reduce to 8. So the maximum stack space, used will be big of weight, because you'll go for 10 depth, reducing 1, 1, 1, you'll go to 10 depth. So can I say this is how you can easily generate for knapsack. So that's space complexity for unbounded knapsack. So how do you convert this into memoization? Again, the same thing. You basically declare a dp of n and w and then you memoize. Very simple. I'm not going to do this any further. What about tabulation? Again, this is something which I'll be teaching. What's the first step? Write the base case. What's the next step? What are the changing parameters? Index and, yes, index and w, right? What's the next thing? Copy the recurrence. That's you do. So let's write the base case. So initially what you do is you declare the dp of n and w plus 1. That's very obvious. And what's the first thing? Write the base case. Let's go and check out the base case. What's the base case? For index 0, w can be anything. It can be 0, it can be 1, it can be 2 till the baggage weight. It can be anything. So for every one, this is what it stores. This is what it stores. Let's write it. For any w, yes, for any w which ranges from 0 to the original w, you can say the weight of the bag or whatever you can call it. You can say dp of 0, because this is the index. W is equal to w by weight of 0. Again, you can take an integer into value of 0. This is the base case. Again, very straightforward, very, very straightforward. So what is tabulation? Tabulation is nothing but bottom up. Tabulation is nothing but bottom up. So in recursion, you did from n minus 1 till 0. 0 is the base case that you've computed. Now with the help of 0, you'll compute 1, you'll compute 2 and so on. So index starts from 1 till n minus 1. W starts from 0 to w, because in the recursion you wrote it opposite, w to 0. So it will be opposite. And the next thing is copy the recurrence. And once you have done this, your code should be ready. So yeah, what are we waiting for? Let's get into the code. So we are given the n, the w, the profit. We can call this as value and this as wt. So let's quickly write a function. So the function will definitely have index, a capital W, and we can definitely carry the val. We can also carry the weight, right? There's something which we can carry, and if index is equal to 0, we return, we do return this, right? We take an integer division of how many items can I steal, which is the remaining w by whatever is the weight of the current 0th index, multiplied by, like, this is the integer multiplication at first, sorry, integer division at first, multiplied with the value, like the number of items. And what are the other cases? There will be cases of not take, where I say I'm not going to take. So the addition will be 0 with the previous index, w, val and wt, and there will be something like take, which will be 0. And I can say if, yes, if w of index is lesser than equal to the remaining w that the knapsack has, so I can say take equal to value of that index plus function. We stay at the same index because it is unbounded, and the w gets subtracted by weight of nothing but the current index, and we can go as val and we can go as wt, and we can return the max of take and not take, because that is what the answer will be. Over here we just need to return the function of n minus 1, w, val and wt. So that's how the recursive code will look like. It does run. So what's the next step? Make sure we convert this into a dp. So vector of vector int dp and vector int and w plus 1 comma minus 1. Make sure you pass that dp over here and just copy paste this particular dp. Again, just make sure you pass it over here with the reference. Over here also you pass it again. Over here also you pass it again. And this will be dp of index w equal to this. and just make sure you write one state check. If that state check has not been done prior to this, you return dp of index and a w. This is how you can easily run it. Let's super quickly run this off. It has run. Let's try to submit this and see if this is running fine. Indeed, it does run absolutely fine. So we have made sure that memoization solution is running. What's the next step? We definitely have to convert this into tabulation. So for tabulation, we look out at the base case. It is for index equal to 0 and w can be anything. So just make sure you write w can be anything from 0 to w less than equal to w plus plus, and at dp of the index 0 and the w, we will just be copy pasting this portion. Very simple. Done. What's the next thing? Make sure you write couple of nested loops. So the couple of nested loops will definitely be starting from 1, will go till n, index plus plus, there will be a w loop which will start from 0 and the w goes till w and w plus plus. And what do? You basically just copy paste this portion. So let's quickly copy paste this portion. Now the next step, just convert this into dp of index minus 1. You make it w. You can super quickly erase this. Over here also just convert this into dp of index, right? And over here w minus w of index, correct? And you can just do this, and right over here what you can do is this portion, and over here you can just return dp of n minus 1 w, and you can just erase this off. And now try to submit this. It is, and let's try to submit the tabulation one. Indeed, it does run. What is the next step? Obviously, the next step is to convert this into two array space optimization. Why? Index minus 1 and index is there. So you're just using the previous row. Again, if you have not seen the previous classes, please watch it out, because space optimization is something which I've taught in the previous classes. So make sure you watch out the previous lectures. So what I just need to do is I need to have something like vector of int previous, right? And we need to have something as cur and w plus 1 and 0. That's what we will be doing. And over here what we can do is this will be cur, this will definitely be previous, right? And what's the other change that we need to do? This will be current, and over here we can write previous equal to current, and this can easily be written as previous. So over here this will definitely be previous, and you can just omit this portion. Now let's quickly try to run this. It has run. Now let's try to submit this off. Now the question arises, can we space optimize this from a 2 array to a 1 array? Because in the knapsack we did a space optimization from 2 array into 1 array. So let's look at the code. What am I using? I'm using a previous and I'm using a current in order to compute the current. So can I say this is the previous? Can I say this is the current? Right? And what am I doing? In order to compute this guy, what am I using? I'm using this guy, which is like, let's write down the lines. Not take is nothing but 0 plus previous of w. Take is nothing but value of index plus current of, if I just write it properly, w minus wt index. Okay. So can I say, whenever you're trying to compute this guy, what are you using? You're using this guy and someone from the current but from the back. Whenever you're trying to compute this guy, what are you using? Someone from here and someone from the previous. Whenever you're trying to compute this guy, what are you using? Someone from here and someone from the previous, because w minus wt is somewhere from here. Whenever you're trying to compute this, you're using someone from here and someone from the previous. Now a simple question to you is, whenever you're trying to compute, let's say this guy, apart from this guy, are you requiring any of these guys? Are you requiring any of these guys? And the answer is no. Why? Because we are just requiring the same column guy. The same column guy. We are just requiring the same column guy. So can I say whatever values, like this value, whatever value I'll get, I'll just rewrite over here. Then I'll move here. Whatever value I get, I will rewrite over here. So can I say I can use a single guy? Single array? Yes, we can, because we do not need the previous values. We just need the same column guy. So use the same column guy, use the previous, compute this, and just put it across here. And you can use a single array, right? For an example, let me just give you, assume this is the previous, just a single array, okay? Assume just this is the previous, and it had some values as 3, 4, 5, 6, 7, 1, 2, for an example, something like this. The moment you came to here and you wanted to compute this guy, for the current row. So what you did was you took 3, like for not take you took 3, for take you looked at the back and you did not find anyone because that's not possible. So whatever is the maximum, you rewrote it. Next you came to here, you took 4, and whatever is at the back, because you have rewritten it, whatever is at the back, you again took it. And again, whatever maximum you got, you rewrote it. Again, you went here, you took the 5, you took someone from the back, and you took the maximum, rewrote it. Just because you do not need the previous values, you can rewrite this value to this guy once you have computed using this particular guy. Thereby, I can definitely space optimize this into a 1D array. So can I say this? If I go back to the code, I don't need a current now. Only one guy will work. Like I can call it as the current guy only. Let's call it as previous to avoid confusion. So I'll just require one guy. This is the previous W. The previous guy, not tick, will be computed. From this previous only, like this is the row which I'm computing because I'm overwriting, so I can take it from here itself. And once I've computed non-take by using the previous value and the previous values, I will take the maximum of that and I'll rewrite it to the W. So the previous W gets rewritten by the max, and eventually you can find your answer. So if I try to run this is also going to run in a 1D array, and you see it is running. Wonderful, isn't it? We started from recursion, exponential complexity, then a 2D complexity, then 2 arrays, then a 1 array. Wonderful, isn't it? So just in case you did understand, please make sure you like this video, and if you're new to the channel, please do consider subscribing to us. And yeah, with this I will be wrapping up this video. Let's meet in the next one. Bye bye, take care.
Whenever your heart is broken.